So we are currently at chapter 3, and we talked about joint probability distributions of more than one variable. We looked at these two variables, random variables. Last week we talked about the concept of random variable, which take numerical values, discrete or continuous, and they are function of outcome of random experiments. So an outcome is turned into some numerical value. It may be the number of heads in a certain number of coin tosses, observing the lifetime of a light bulb, and things like that. So today I'm going to talk about some properties of these random variables. For example, when we do this experiment, what is the expected value of a random variable? Or if we observe some outcome or some random variable's value, is it unexpected? How things like that. Or in this experiment, how variable is this random variable? Is it all around some average number, or is it all over the place? So we are going to learn expectation and variance and some properties of expectation, like its linearity, the expected values of random variables which are linearly combined or multiplied with some constants. So we are going to talk about these today. And before we start, I have a couple of small announcements to make. First, your first assignment is being prepared by one of the teaching assistants. So he is going to announce it probably by the end of this week on Friday. And you will have about 10 days to work on it. It's similar to the quiz question, but maybe 2 or 3 of such quiz questions. You'll be able to, it's very simple. You probably need 1-2 hours to work on it, but it's going to be prepared in LaTeX, and the template for you is going to be provided. So you're going to write your solutions in LaTeX, but we are going to provide you a template. So it's going to be, its duration is going to be about 10 days. But as I said, it's a very simple assignment that you should be able to do in 1 or 2 hours at most. Okay, two questions similar to what you're going to be seeing also in the midterm exam. This leads me to the other announcement. The midterm exam, we have tentatively submitted our request to the submitted our request to the department to be on April 29. Okay, so here let me mute you all. There's some noise in the background. Okay, so it's tentatively set at Thursday, April 29th, which is about 1 month from now, at the end of week 7. Okay, so we will be, after we finish, no problem. After we finish April 7th week, we are going to have our midterm exam in the evening. It's going to be like a 2-hour midterm exam, and you will have to have your cameras on. So there will be teaching assistants that are proctoring the exam. We are going to send the details about how the exam is going to be conducted, but you may mark this tentative date. I mean, unless there's some collision with something else, this is going to be set at that date. But since, as I said, the different courses submit their request to the department, and the department just takes a look at them and decides which course is going to be when, which exam is going to be when. So this is what we have submitted, but it's not certain yet. But just I wanted to give you a heads up on what to expect about the possible midterm exam date. Also, in order to be synchronous with the other classes, I made a small modification to the schedule, which is chapter 5, the simulation of random variables. It was actually right after chapter 4 in my schedule, but in syllabus it was at the end of the semester. Okay, so, and the other 2 sections are also doing it like that. So I moved week 6 to week 12, the simulation of random variables, the Monte Carlo methods. We are going to see these chapters 5 and 6. 6 was already at the end of the semester, but chapter 5 is also moved to the end of the semester. So this is a slight change. So we are going to directly jump into statistics after we finish these continuous random variables, continuous distributions. Okay, so after we finish chapter 3 and 4, we are going to then go to statistical inference, hypothesis testing, confidence intervals, and this stuff. And probably the midterm is going to be at the end of 7th week. This is how we planned it, right? So these are just some small announcements about the course conduct. Any questions or comments? All right. So let's continue with today's class, which is the chapter, the expectation and variance. So we have talked about, remember, we have talked about these joint distribution table for two random variables. The joint probability distribution contains all the information actually about these two random variables. If we are given all the intersections of these events, for example, when x is equal to 0 and y is equal to 0, and x is equal to 0 and y is equal to 1. These are mutually exclusive and they're all exhaustive events if what we have in this table are all the possible values y can take and all the possible values x can take. Okay, if these are the possible values this random variable x can take, and these are the possible values the random variable y can take, this entire table, these are a bunch of intersections, and they collectively span the entire outcome and random sample space. So they are exhaustive. And since x cannot be 0 and 1 at the same time, these are mutually exclusive events. All these intersections, they are mutually exclusive and exhaustive. So for example, if you want to figure out what is the probability of x is equal to 0, we can sum up the values in the entire first row to find what is the probability distribution, individual probability distribution for x. The probability that x is equal to 0 unconditionally is 0.5. So x is either 0 or 1. It's like x is like throwing a single coin, and the outcome and the random variable may be the number of heads when you throw a single coin. Okay, so x may be such an event. And y takes these 4 different values, and here we see again we can sum the columns to find the summing up these rows actually directly follows from the law of total probability, because x is equal to 0 and y is equal to 0, x is equal to 0 and y is equal to 1. These are basically mutually exclusive events, and we are summing over all the values 0, 1, 2, 3, y being 0, 1, 2, 3, covers the entire, they're exhaustive and they're mutually exclusive. Then we can sum all these up to find, by using the law of total probability, to find what the probability of x is equal to 0 is. All right, so this is, the table is given to us only this, if 2 by 4 table. So this joint probability distribution table tells us we can compute everything from there. Most of the time, when there are more variables, so when there are 2 variables, it's okay. We can fill in this entire table. But imagine you have a machine learning problem where you have 50 different random variables, 50 different features you measure, observe for a certain object. Having this joint probability distribution is very prohibitive in that case. We cannot, a 50-dimensional table is going to be exponentially large when all these, imagine if some of them are continuous. When we have continuous random variables, we're not going to have a table like this. We are going to, each row here is going to be like a function, a 2-dimensional function, and it's going to be like a surface if you have 2 variables. So these are not going to be individual table entries, but we are going to be given some continuous functions in that case, which will collectively form a surface. And when we have more than 2 variables, this is going to be a surface in higher dimensional space. So that's why it's difficult. But in this course, we're not going to discuss more than 2 variables at the same time. Okay, but if you take other technical elective courses later, like some machine learning or deep learning courses, or some image-based computer vision courses, you're going to see that they are going to refer to such probability distributions a lot. Now, let's talk about expected value. When we have a random variable defined, what is this expected value? So, for example, if you toss the coin 5 times, let's assume we toss the coin 5 times. What is the expected value? And my random variable x is defined as the number of heads. If I have number of heads is x, all right? So the possible values it can take is from 0 to all the way to 5, all right? So I picked a more difficult one than 3 coin tosses, 5 coin tosses. Now, x is the number of heads. It can take values here from 0 to 5. What is the average value? So when you think about this, the average value seems to be, I mean, you would expect, since we expect head and tails equal amount, intuitively, you directly go to 2.5, right? I mean, that's probably the correct answer, 2.5 heads. So the expected value of a random variable, the expected head count when in 5 coin tosses is 2.5. As you can see, it's not an integer. It may be the expected value can be a real value like 2.5, because it's the our average expectation. And the way it is computed is not just the average of these 5 numbers. The way expected value is computed is taken into account the probabilities of all of these things. For example, you will get the x can be 0, but with what probability? So probability that x is equal to 0, we need to take into account this when we are taking the average. So the expected value of x in this case is going to be computed by making a weighted average of all the possible values the random variable can take, okay, plus 5 times the probability to observe 5. So what is the problem? And these weights here are going to be the probability of x to be 1, all right? The probability that x is equal to 2. So these weights, as you can see, it's a weighted average because they all add up to 1. And then since this is a probability distribution, these probabilities at the end should be exhaustive. We are looking at all possible values of values the x can take. So we are going to do a weighted average of these values it can take, weighted by probabilities. Okay, so for example, what is the probability that we're going to get 0 heads? Actually, it doesn't matter. Whatever this probability is, we're multiplying it with 0, right? So this is, we're going to get 0 from here. And from 5, what is the probability that we're going to get 5 heads? It's going to be 1 over 2 to the power 5, right? All of them being heads, it's this probability. If they're all outcomes are equally likely, the probability to get 5 heads is only can be obtained with from a single outcome, which is head, which is with an associated probability this, which is 1 over 32. Okay, so 5 divided times 1 over 32. Now, what is the probability that we're going to get 1 head? There are 5 outcomes in which we can obtain 5 heads, so it has to be 5 over 32 if I'm not mistaken. But again, here this also should be 4 times 5 over 32. And what about 2 and 3? They should also have equal probabilities if I'm not mistaken. But what is the different? So this goes into that combinatorics chapter in section 2.3. So what is the different, how many different outcomes out of all these? What you can do is you can list all those 32 outcomes and count in how many of them we have 2 heads. Or you can combinatorically figure out. I think it's probably, so this is 6, this is 6, 12, 20, I think it's 10, right? 10 over 32. In 10 of them. So if these 2 are equal, it should be like this. Okay, so if you I mean, just let me know if I did some mistake here. So what is going to be? It's going to be 5 over 32, 20 over 32. So 5 over 32 plus 20 over 32, another 20, oh, then this is 30 over 32. I multiplied with 3, and another 20 over 32, and finally another 5 over 32. So what I did was, so this was 0, I didn't add it into the summation. 1 times 5 over 32, 2 times 10 over 32, 3 times 10 over 32, 4 times 5 over 32, and 5 times 1 over 32. If you add all these up, let's see, 90, so is it, no, 70, 80, right? It's in total, so this is 40, 70, and 80. 80 over 32. What is it? It should be 2.5, right? So 64, another 16. Yeah, it's exactly 2.5. So this is how you can find that the expected value is indeed 2.5 by with a weighted average of the values it can take over weighted by with the probabilities. So this is how expected value is defined. In continuous case, in continuous random variables, we are going to take, and this summation that we have is going to be turned over for all values of x can take from minus infinity to plus infinity. We are going to have its the probabilities. We don't have individual probabilities of variables, but we will have the probability density function. So we are going to multiply the values the x can take with this. So this is also like a weighted average. We are weighting the values of x now, this time with the probability density function. And if you sum this over all possible values of x and the probabilities, for example, if this probability density function is 0 in certain intervals between this minus infinity to plus infinity, this is going to just be 0 for that. So what we had in discrete case is for all values x can take, we had the summation, right? The probability that x is equal to x. So this is what we have. The expected value of this capital letter X is equal to, for all x's that this x can take, we do a summation, a weighted average. This is the weighted average summing up these values of x multiplied with their probabilities. So this is the discrete case, and it directly turns into then integration. The summation will be integration in continuous case, and we are going to see more details of these later. Right now, we're just focusing on discrete random variables. Okay, so this is what expected value is. So let's see. Yeah, so this is what we have also in the on the slide. The expected value is sometimes, I mean, most of the time, is indicated by this Greek letter mu. Okay, which means which is like an acronym for mean. Okay, or average, mean average. So this Greek letter mu is used to indicate the expected value of a random variable. And it can be thought of as the center of gravity of the distribution of x. For example, in the continuous case, you may think about if this is like our probability distribution here in continuous case, if you think of this, the center of gravity, if you want to balance this at some point on a scale, where would where could it be balanced? That's where your mu is. All right, so it can be thought of as the center of gravity of the distribution. So it's not always the exact geometric center, depending on. So if this probability density is made up of some homogeneous material, some same kind of wood, you can think of it as the total weight of this wood is 1 kilograms. And where would you put some balancer so that it's going to be balanced on the left and on the right? All right, so this is what the expected value of a random variable is. Now, I'm going to now go to, so the expected value has certain properties, like the linearity of expectation. So, which is this, let me write it, it's not this one. Let me write it here. For example, if I know the expected value of some variable is, for example, mu. Okay, if I ask you this, what is the, let me define another random variable, which is 3x. Okay, so if I multiply this random variable by 3, and what would you think the expected value of this will be? I mean, it's maybe a very simple question, right? It seems obvious, like 3 times m. I mean, if you multiply this with 3, I mean, if the expected value of this random variable, the same random variable is mu, if you multiply it with 3 times, of course, the expected value is going to be also multiplied 3 times. You may also try to prove it mathematically, but in general, this is called the linearity of expectation. If we have a linear function of multiple random variables like this, bui times c, okay, the expected value of this linear combination of random variables multiplied, some of them multiplied with some constants, and some constant is added, is equal to a times the expected value of x plus b times expected value of y plus c. All right, so we can actually just put these expected value inside this variable, and just if you compute the expected value of x individually, y individually, and then compute this final linear combination, that will be the expected value of this thing. All right, so there are some other properties. If you have a function, that's also another interesting thing, especially in continuous case. If this is more general, that function that I showed you on the whiteboard was a linear function. Okay, if a linear function of x is just like this, but in general, if you have any function of x of your random variable, if you just put your random variable x into some function, yeah, let me look at the question. Can we calculate one parameter's expected value in a 2-parameter function? Okay, that's a good question. So what you mean is that if we have two joint, what is the expected value, for example, of joint probability distribution? So when you define 2 random variables x and y, okay, so what is the expected value of, for example, you mean x times y, or I mean, this is, for example, non-linear. When we have 2 random variables like this, the expected value of these 2 things will be a little bit complicated. So we are going to come to that, but it's not necessarily their multiplication will not necessarily be, we cannot use individual expected values to solve in this case. All right, so that will be more complicated, and we are going to come to that. But right now, just know the linear combination of these multiple variables. If you have 2 functions like this, if you linearly combine them, like if you just do this, again, it's 2 parameters, okay? But it's a linear combination of those. And in that case, a linear combination could be just chopped up into individual pieces and computed separately and then combined later, okay? This is called the linearity of expectation. It only allows, I mean, we can compute expected values only as such. In cases like this, this is more complicated because we may need to think about their joint probability distribution. This doesn't assume anything about their independence or anything, okay? So this x and y variables, they may be independent, dependent, it doesn't matter. If we have a linear combination of them, it can be directly written as such. But when we have a combination of 2 random variables combined in a different way, for example, it could be x to the power y, okay, then it's really more difficult. We may need to, again, we are going to do it like this. Again, it's going to be a summation. This time it's going to be, for example, if they're continuous, it's going to be a double integral over all possible values of x and over all possible values of y. And you're going to write x to the power y here. And the probability that, and we are going to have a 2-dimensional function this time, fxy dx. All right, I think this is what you're actually asking. So we need to write the whatever function they're related with, you're going to write it here like this. This is the value of the, if you just give some individual values. So these are capital X and capital Y, but these are lowercase x and lowercase y. For all possible values of x and y, we are going to write that function you have here, and we are going to write the probability, the joint probability of x and y together to compute this. Again, it's going to be a weighted average, but the interesting thing here is that this function here, the joint probability is multiplied with your values, and since these these may not be linearly separable, that's why we cannot write this in general. We cannot do that. E to the power x to the power e to the, we cannot write this for this case. Okay, this is not true. This x is it's not allowed. It's not true. Okay, so we cannot just separate these exponentiation or multiplication. We need to compute it individually by double integrals or double summation. In the case of discrete random variables, we are going to take a look at all possible values of x and y. We are going to write it like this, and probability that x is equal to x and y is equal to y. Okay, again, the joint probability. But that's a very good question. We are going to, because in that case, you see, we are multiplying. Again, they're weighted, but the summation is now over the entire values of the table, and the weights are now the intersection. X is equal to y and y is equal to y weights. So it's going to be computed like this. But this is how a general solution can be obtained by going over all the possible values together they can take. Thank you. So yeah, when you have, these are some small other functions. So even if, for example, the expected value of x squared in this case, for example, is not just, you cannot take the expected value of x and square it, all right? Because this is not linear again. This is not a linear function. You need to compute this x squared fx if x is discrete. We can actually try it, for example, on let's see. In our case, let's go back to the coin toss case, but this time let's toss 3 coins where the expected value of x is 1.5. Right now, what is the expected value of x squared in this case? What I'm saying is that it may not be equal to, maybe in this example it may be, but in general, it is not equal to this. Okay, so it shouldn't be equal to 2.25. All right, so this, when you square it, it's 225, right? Did I do it right? Let me just check that. Yeah. 1.5 times 1.5, yeah, 225. So it shouldn't be. So how are we going to compute then expected value of x squared? We are going to do it like this. The 3 coin tosses, the possible values x can take is 0, 1, 2, 3, right? So what we are going to do is do the summation. 0 times, actually 0 squared times the probability that we are going to get a 0 plus 1 squared 3 over 8 and 2 squared 3 over 8 and 3 squared 1 over 8. Let's compute this one. So this is what I have written here is the expected value of x squared, where x is the number of heads in 3 coin tosses. Oh yeah, in plain English, it's going to be the square of the number of heads. Basically, it may not have I mean, it's just a randomly defined toy example which may not have any meaning in terms of random variables. It's just like the squared number of heads in 3 tosses. Okay, so squared number of heads in 3 coin tosses would be what it would mean in English. Which I mean, why would you define such a variable, you may ask? I mean, maybe in this case it doesn't have any meaning at all. but in certain cases it may have a meaning. Oh, this 1 over 8 and 3 over 8 for 3 coin tosses. The probability to obtain, so there are 8 possible outcomes. So I immediately use this 1 over or 3 over 8 from last week's classes, sorry. But while we compute that there are 8 possible outcomes to obtain 0 heads, only one outcome is associated with 0 heads, and only one outcome is associated with 3 heads. To obtain 1 head, there are 3 outcomes in which H, T, T, A, T, H, T, and T, T, H. So these are since each outcome is equally likely, if we have 3 fair coin tosses. So out of all 8 possible outcomes, this 3 gives me the random variable 1 head, and therefore it's 3 over 8. And vice versa. This is, the only remaining thing is the other 3 over 8. So this is what we get. So let's see whether it's 2.25. I'm not exactly saying that it's all the time they're not equal. Some cases, by luck, you may get them equal, but in general, this is not true. I hope this example is one of those not true cases to show you that they're not equal, but if it turns out equal, it doesn't mean that all the time they're equal. All right, so let's compute this. So this one is already 0. This one is 3 over 8. 4 times 3, it's 12, right? 12 over 8 plus 9 over 8. So let's add these up. 24 over 8, right? Am I mistaken? So 12 here, 24 over 8, and it's 3. You see? I'm glad that it's not equal to 2.25. So it's 3. So the expected value of x squared in this case, when we have x is equal to the number of heads, turned out to be 3, not 2.25. Okay, so we have just shown with an counterexample that x squared could not be written like this. So if you want to compute a function of an expected value, you have to write that function here and multiply again, do a weighted average of that fx, not fx, this was gx, whatever that function is. If it's x squared, if gx is x squared, you multiply gx with the probability that x takes at that value, and then compute the expected value of that function. All right, so these are they may look simple, or but these are really important stuff. Okay, we will be doing lots of computations based on this expected values. So if you understand these foundations and if they're solid, you will do very well in the upcoming weeks. Now, let's I talked about this linearity of expectation. If for any 2 random variables or any arbitrary number of random variables actually and some constants, their linear combination can be taken out. So the linear function, actually it could probably be proven mathematically by using the original. If you replace that gx with some linear function at the end, what you're going to get is you can take out of this summation, whatever function you have, those could be taken out of the summation, or the summation could be chopped up into 2 pieces and summed up individually. This is what it's basically saying. For example, so it's very simple in the case of just multiplication with a constant, right? For example, if gx is c times x, all right, if I have this, what I'm going to have is sum over all possible values of x, where you have cx probability of x is equal to x. Okay, if you have a summation like this, we already know that constants in summation can be taken out of the summation, right? So it will be c times x px is equal to x. And what is this? This is the expected value of x. So this is basically saying that expected value of cx, which is this, is equal to c times expected value of x. So this is how you can mathematically prove when you multiply a random variable with a constant, it falls like this. You can do the same thing for summation, so which will lead you to any linear function of random variables could be individually computed. Yeah, and this is what Hassan asked actually, the expected value of a product, for example. In general, not only product, the square, in general, this is not equal to, since this is not a linear function, x times y is not a linear combination of x and y. So in general, this is not equal to ex and ey. In order to do that, we need to compute this over all possible values of x and y. This is your function gx, which takes two parameters, x and y. This is your function gxy, which takes two parameters. And you write your gxy here, and you go to the joint probability distribution and compute this to find the expected value. All right, now let's come to something interesting. Okay, this was the expected value was one parameter of our random variable. The other is, we usually wonder, how variable is this random variable? For example, if you think about the grades the students have from one class. If I say, for example, the average grade in this class is 50, all right? In class, let's call this class A. In class A, the average grade is 50. In class B, the average grade is also 50, okay? So this by itself is not sufficient to understand how the grades are actually distributed. It tells us that the center of gravity, the average grades are 50 in both classes. But in class A, maybe most of the students took grades like 49, 50, 51, 49. It may be all the grades are between like this, all right? If there are, for example, 12 students in both classes, if these are the grades the student takes in class A, the average is going to be 50, and this tells me that most of the grades are close to 50. And maybe in class B, it may be something like this: 10, 50, 90, 10, 50, 90, and another all 10, 50, 90, maybe even 5, 50, 50, 95. Okay, look at this. I mean, these are all very closely together around 50, like this, if this was the histogram. And in this histogram, we have like three modes, but here the average, if you sum them up, and if you just divide, so if you average them, you're going to get 50 in both cases. But in this class, the grades are really variable. There are very low grades, very high grades, also average grades. So this is different in these two cases. So when you say the grade you get from this class A, let's call this variable x, and the other random variable y, the expected values are the same, but when you get a grade of 10, for example, in this case, when in class A, when a student gets a grade of 10, we are going to be surprised, right? Like he's going to be an outlier in the class A. But if the random variable y takes the value of 10, we're not going to be that surprised, because there are lots of, I mean, 1/3 of the class takes grades like 10, 5. So this, when we see a grade like this here, we're not going to be surprised. But when we see a grade like this, x is equal to 10, we are going to be surprised. So how can we get this feature of the distribution into account? So what is that thing that tells me how differing, how variable the random variable is? Okay, so the term for that is called variance. Actually, what we're wondering this: what is the expected value of x? How does it differ? What is its difference? So if you look at mean, the mean value is 50 right here. And when we get a random variable x, how is it different from mean? So what is the difference from the mean? In this case, the difference from the mean is like 1. It's very close. But here, when you get a random variable y, it's different. Let's call them mu x and mu y. This difference from mu y is maybe a lot. So what is the average difference between these two things? This is what I wonder actually. But here is the problem. This is going to show you why variance is actually squared. First of all, if you directly write something like this, I may be wondering the difference between the random variable and the mean of that random variable. It's because this is going to show me how variable it is, right? But this equation has some problems, right? Because the result is always going to be 0. Because no matter how variable x is, this is always 0. Why? Because of linearity of expectation. This is a constant. Mu x is a constant that we have computed. It's the average. So it's the expected value of x. So if you try to find the expected value of this difference between the random value that it takes and it's the center of gravity, if you pose the question like this mathematically, it's always going to be 0 because of linearity of expectation. Why? Because it's going to be written as expected value of x minus, since this is a linear combination of these two things, expected value of mu x. Since this is constant, what will happen is this is equal to mu x. What is this? This is also equal to, the expected value of x is mu x. This is how we define. So mu x minus mu x is always going to be 0. So this is not the way to compute the difference. And therefore, one way to compute it, why do we compute them directly? Why don't we make it a function, which is not going to turn out to be, for example, what will happen if I take the square of both things? Or let's see, whether this is what they tried this. Okay, yeah, actually not the square of things, but what is the expected value of the difference squared? The difference squared has some benefits. First of all, it's always positive. So here the variance is defined as the expected value of this square of the difference. Because when we directly look at the expected value of the difference, sometimes it may be negative, positive. And we cannot use absolute values here because absolute value also has mathematically it's very difficult function. You have to piecewise treat it differently. So absolute value is not linear. So absolute value functions are more difficult. So taking the square solves lots of things. First of all, we are going to measure this variation or difference always as a positive value. Okay, so whatever value we have here, since it's squared, even if it's negative, we're going to get something positive at the end here. And if you write this function as a linear function, it's going to be something like this, like expected value of x squared minus 2x mu x plus mu squared, right? Mu x squared. So if you write it like, if you just open up this square function, it's going to be this function, which is like a linear combination of multiple things, which you can then write expected value of x squared, then minus, so this is really like a linear function, minus 2x mu, so this is, I need to write expected value of x mu x. Okay, so this, what you have here is a linear combination. So I can directly take out these constant numbers outside, or if you want me to combine them together, these were the constant numbers, 2x mu x and expected value of x here, plus this is a constant number, so its expected value is going to be the same thing. So if you look at this, I can replace this with mu x. So it's expected, this entity here, I'm going to move on to this side, expected value of x squared minus 2 mu x squared, minus 2 mu x squared and I have plus mu x squared there, which they can nicely cancel to. Ex squared minus mu x squared, the standard formula for variance. Okay, so in order to find the variance of some variable, you first, all you need to do is find the expected value. This is ex, and find the expected value of the square. Oh, now it may make sense of why we square random variables. Okay, why we want to find the expected value of a square of the expected value of a random variable. So this is exactly what the same thing we did for 3 heads. So for example, what is the variance in the case where we throw the coin 3 times? The expected value of x squared was 3, right? If you remember 24 over 8, it was 24 over 8. This was the expected value of x squared, and mu x was 125. No, 1.5, and 2.25 was its square. So what I have here is the variance of x, where x is the number of heads in 3 coin tosses, is going to be 0.75, which is this difference that I just computed here. So in other words, the square of the difference between the random variable and its expected value is simply, first you open it like this, and by using linear of expectation, you arrive at this formula, which is you have, in order to find the variance, if you want the square difference between those things, the expected value of this square difference is the expected value of the square root of that individual random variable minus the square of its expected value. So this is what we call variance. So variance is like the square of this distance. If you want to get into a unit, so its unit is whatever the unit your random variable has. For example, you may have been computing the grades, for example. Its unit is the GPA, okay, from the grade point average. It's what its unit is. Or if, for example, you are measuring the weight of some fishes here, the unit of the random variable may be kilograms, okay? And as you can see, kilogram, and this unit is also kilogram, the unit of variance will be kilogram squared. Okay, so what I compute here is the expected difference of my random variables from their average distance squared, which is kilogram squared. So if you want to ask what is the average difference in terms of the units of kilograms, you need to take the square root of this thing. So 0.75, if you take the square root, it's what it's going to give you is called, you probably know this a lot, standard deviation. So this is what standard deviation is, which is the square root of the variance. So if my variance, if the variance of x is something, for example, a, the standard deviation, which is usually indicated by this, again, Greek letter sigma, lowercase sigma, the standard deviation of x is the square root of the variance of x, and its units will be the same as the units of your random variable. Okay, so this way we get ourselves the average difference, again, always positive. Okay, the square root of this always positive number is also going to be positive. So a way to measure the change of my random variable from its mean gives me the standard deviation. So these variance and standard deviations are used a lot to give an idea of how a random variable changes. So this is a single slide here. We have standard deviation defined as the square root of this. And this is not, the slide directly gives the formula for variance, but I have just shown you how this formula can be obtained from linearity of expectation by just first opening up the square into a linear formula like this. But these are not linear functions, so I cannot make it ex times ex. So x squared is not a linear function, so I have to compute this one. But if you look at the remaining part of this, it's all a linear combination of my random variable x or some constant. So this is how we get to this formula that is on the slide to compute the variance and standard deviation. Yeah, you can try this example though. So this is two coin tosses. What is the expected value of the, oh, no, not coin tosses, this is dice, okay? Two fair dice are tossed. What is the expected value of the random variable of x? So in this case, the possible values you can have for that random variable starts at 2. The smallest you can have is 1 and 1. So it can take all the values from 2 to 12. So first you need to find the expected value of the dice by summing over all the possible I'm computing the probabilities from 2 to 12, 2, 3, 4, 5, 6, all the way. You get 6, 6, which is the summation is 12. Okay. Or can you also do something like this? So the two fair dice are tossed. If I can separate these two dice and the random variable they have here on top of them, can I represent this x random variable as a summation of two other random variables? And if I compute their expected values individually, can I compute the expected value of some by using their expected values? It could be done actually, but in terms of the variance, because since we're so then in that case, you need to figure out a way to compute the expected value of x plus y squared, which is going to be difficult because you're going to have a term that has a multiplication of the two random variables. In that case, you need to go back to the joint probability distribution table. So you can do both ways. Try to solve this example, okay, by until Thursday. I'm going to solve this example on Thursday, but as an exercise, try to do it yourself. And then we are going to continue and finish this on Thursday and going to start talking about, so I have only like 3-4 slides left from here. We are going to start some discrete probability distributions, some certain widely used discrete probability distributions on Thursday. All right, that's it from me for today. I'm going to stop recording.